So when a signal is modulated, we modulate it with the corresponding frequency of that channel. So when demodulating it back, I have to multiply the signal. The LO, the local oscillator, should give you a carrier frequency of that same channel frequency, the center frequency of that channel. Okay. So a receiver will, if I have a fixed LO in a receiver, that receiver will work only for a particular channel. But you know that the whatever different sets, receiver sets we have at home. For example, you have a radio, you have a television. They are for general purpose. They are supposed to receive signal from many channels, multiple channels. So your receiver has to be designed so that it can receive signals from multiple channels. Okay. In this case, I have written that since I am talking about radio broadcasting, it should receive signals from multiple radio broadcasting stations. Okay, and then accordingly I have to listen to only a particular broadcasting station. Now your antenna, which is there in the air, it will catch all the signals from all the channels whichever is present there. Okay, whichever whichever channel signal is present there, the antenna will catch it. But now I have to make a selection. Okay, I have to make a selection. So antenna will be connected, because antenna is picking up all the frequencies. So antenna has to be connected to a tuning circuit. Okay, and then it will be followed by a local oscillator. Both of them, the local oscillator and the tuning circuit, has to be tuned to that particular desired radio station frequency, Fs, which is the carrier frequency of that radio station. So it is actually the center frequency, because you know that, as I have shown in one picture earlier when I was showing the frequency division multiplexing, I have shown that is one channel. So basically this channel or the radio station is not just one frequency, it is a band of frequency. But the frequency that we talk about when we say that this channel is of so and so frequency, you will always see that it is say 98.4 kilo megahertz FM. That means that is the center frequency of that channel. It cannot be a single frequency. It has to be a band of frequencies for a channel. But the frequency that we mention for a channel is basically the center frequency of that channel, which corresponds to the carrier frequency that we are using for modulation and demodulation. Okay. So when I'm saying about all this channel frequency Fs, that means it is the corresponding center frequency of that channel, which corresponds to the carrier frequency of that station. Okay. So I have to tune the system. So basically this is, I have to have a resonating, I have to have a tuning circuit. Okay, I have to have a tuning circuit which should be tuned to that particular radio station. Okay. So sorry. This tuning circuit, so the antenna is catching signal from all the channels, but then there will be a tuning circuit which will select only the signal corresponding to the Fs and its adjacent. Okay, so it will be tuned like that. It will tune to Fs, means it will catch signal from Fs and its adjacent band. Okay, this is one example of a LC tuning circuit. L is your inductor, C is your capacitor. So your Fs, you have to design your L and C in such a way you get it tuned to this frequency. Okay, this will be the tuning value. Okay, tuning frequency value. So at this frequency, this tuning circuit resonates. Resonates means this one, essentially this L and C combination, this essentially becomes open circuit. Since it is open circuit, at this frequency, all the signal you will be getting it at this output, you will be getting it. For all other frequencies, for all other channel frequencies, this LC will act as a short circuit. So all other signal from all other channels, they will go to the ground, short circuit. They will go to the ground. You cannot receive it. Okay. Only signal corresponding to this frequency and its adjacent band, that only can be received at the output of this. Okay, at this point, that can be received. All the other signals will be shorted to the ground, so they will be not received. So that is how the tuning circuit selects only a particular channel, signal of a particular channel. That is how it selects. Now, here I have shown that for selecting a particular channel, I can change my FS by changing the C. We generally don't change L, we change only C. We change this C. How it is done? Now it is done by a capacitor like this. It is a parallel plate capacitor. You know parallel plate capacitor, you have studied. There is one plate like this, and the other plate is rotating. This is a fixed plate and this is a rotating plate. Okay. Now when you have the knob, okay, nowadays you don't use knob, you use remote control button. But earlier days when we used to use the tuning using the knob, we used to turn the knob for tuning. When we used to turn the knob for tuning to a particular radio station, then this movable part of this plate, that will be rotating, okay, over this plate, okay. And I have shown it was shown two other positions of this plate, movable plate. When it is in this position, there is no overlap, okay, no overlap between the plates, so there is no capacitance. You know that capacitance value will be proportional to the area of that overlapping plates. The two plates, parallel plate capacitor, you have your capacitance equal to epsilon area A divided by distance D. D is the distance between the two plates. Okay. D is fixed here. Epsilon is fixed here. So A area is only changed. Here you see the overlapping area A is 0, so no capacitance. Here it is 50%. So it is midway, the capacitance. And here you get the maximum capacitance. So by rotating this plate, we change this C, and accordingly this Fs value changes. Okay. So this is how the tuning is done. Okay. Now for better selectivity, obviously, if I have only one stage of this tuning circuit, then it may not give you very good selection. The selection may not be that good. Again, the reason is this one. When I am selecting a particular band of frequency for a particular radio station, this band pass filter I am using, okay, basically that LC tuning circuit is acting as a band pass filter. It is acting as a band pass filter. Now, when I am doing this, you see that the selection is not good here, isn't it? Because there are something like this. I want my selection to be exactly within this F1 to F2. This is my channel band. F0 is the channel middle frequency. Okay. Fs. This is my Fs, channel frequency. Radio station frequency. This one. And I want F1 to F2. But because of the practical reason, this filter will not give you good selection. Here there will be some value of adjacent channels will also come. Okay, they will come. They will be interfering. Okay, so what I can do now, you see here actually the gain of this filter at this point. Okay, it is gain is equal to 1. Gain is equal to 1. Here the gain is less than 1. Here the gain is less than 1. Okay, but there is some gain. So suppose at this point the gain is 0.5. Okay, so some signal corresponding to this frequency is coming, but 50% of it, 0.5 is the gain. Okay, so now if I have two band pass filters, one after the other, then you see that signal corresponding to this frequency, the gain is 1 into 1, 2 times it is multiplied. So that signal is good. There is no change in that signal. It is not attenuated at all. But the signal which I was getting at this place, which was 50% earlier, now it is 0.5 into 0.5, it becomes 0.25. So this signal is now attenuated more. Okay. So the adjacent bands can be attenuated more and more if I use this band pass filter one after the other again and again. Okay. So this is how you can do a better selection. You can reject the adjacent bands gradually if I do band pass filtering more than one times, multiple times if I do this band pass filtering. So that is what we do here, that we do band pass filtering multiple times. So you see here I have shown here dot 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 dot. So that means multiple times I am doing this band pass filtering, and by doing that I am able to have a better selectivity. Now the problem, this type of radio receiver, this tuned radio frequency, this used to be called tuned radio frequency receiver. This was used sometime during the second and third decade of the 20th century. Okay. However, the problem here is that if you have multiple stages like that, then in every stage I have to do the tuning. I have to first tune this, then I have to tune the next stage, then I have to tune the third stage. So I have to do the tuning for a long time. I have to spend in doing the tuning in multiple stages. Okay, so that will take some time. Okay, so that means it was not very good, because manually you are doing this tuning for every stage separately. That was not good. So to take care of that, something like this, it is called a gang capacitor. This came into existence afterwards, where multiple capacitors like that are ganged together on a common tuning shaft. This is a common tuning shaft. So when you turn this one, the capacitors of all the tuning stages will be all the capacitors will be accordingly adjusted. All of them will be adjusted all at a time. Okay, you can see that basically I am putting the same capacitor, multiple capacitors. Here I have put 4 capacitors for 4 stages of tuning. Okay, all of them placed on a common shaft. So when I turn the knob, I do the tuning of for all the 4 stages together. Okay, however, that gang capacitor and all these things came in, was developed later on. But even before that, a better method of radio receiver system was developed, which is called super heterodyne receiver, which is even now, that is the receiver system that we use. Okay, not only in radio system, even in television system and other communication system, this super heterodyne receiver is used even today. Just a basic idea about what is super heterodyne is that I want to have a better selectivity. Means I want to select my desired channel and cut out all the adjacent channels. I want a very, very good selectivity. That is basically my idea. Okay. Now the problem with selectivity is that at lower frequency, you will study about it afterwards, why it is so. At lower frequency, the filters, they give a very good selectivity. But at higher frequencies, it doesn't give a good selectivity. The selectivity is bad at higher frequencies. Now, when I am operating one receiver over many channels, that means for a lower frequency channel, my signal quality will be good because there the selectivity is good. But when I am trying to receive signal for a higher frequency channel, my selectivity is bad, the signal quality is bad. So I am not having uniform performance. The performance over different channels is not uniform. My receiver is good only for lower frequency channels. So super heterodyne receiver was developed to take care of that. What it will do is that in the first stage, whatever is the signal frequency, whatever is the channel frequency, it will pick up that signal and convert it by using the tank circuit and LO, just like what we were doing earlier. We will convert it not directly to the message signal frequency. We will not do the demodulation directly. We will convert it to a lower frequency, somewhere intermediate frequency. Okay, message signal, as we have seen, that message signal will be the baseband, the low frequency signal. Modulated signal, the channel, whatever the channel is transmitting, that is a very high frequency signal. So what we do, we first bring down the frequency from FS to some intermediate frequency, FIF, and then this FIF is fixed. In a receiver, this FIF is fixed. This is fixed. And then in the second stage, I do the demodulation for this IF frequency signal. Okay. So if you see that picture, the picture is like this. All frequencies are present in here. The antenna is receiving all frequencies. Okay. But I have a tuning stage here, that LC tuning circuit. It will receive and select only FS, and maybe some adjacent signals also will come as spurious signals. They will come just interfering it. So, but mostly I have tuned it to FS. So FS is the main signal, and some adjacent signals will be just coming as spurious signal. Okay. Now what I do, I use a local oscillator, and the local oscillator frequency I will adjust it. This will be, both of them will be tuned together. Okay. I adjust it. So I have to do the tuning here only. Okay. I have to do the tuning of this RF amplifier along with the local oscillator. And the local oscillator frequency will be selected as FS minus FIF. This FIF is fixed. So whatever channel frequency I am selecting, whichever channel I am trying to receive, accordingly the LO will be also selected. Okay, this tuning circuit will be adjusted to that, LC will be adjusted to that, and the local oscillator LC also will be adjusted. Local oscillator, different local oscillators are there, different types of them. Some of them also use LC. So suppose it is using LC. So here also the capacitance and all these things will be adjusted accordingly, so that this local oscillator produces a signal of frequency, this FLO equal to this. Now when these two are multiplied, it will produce a signal FIF. It will produce a signal FIF, which is equal to FS minus FLO. Okay. So this is, now whatever is the station, whatever radio station I am going for, whether it is channel 1, channel 2, channel 3, channel 10, whatever it is, in all cases, at this stage, the frequency is fixed to FIF at this stage. Now from this stage, I have again a tuning circuit for better selection. I will be having an amplifier. I will be doing the demodulation, everything. And now you see all this part of the circuit, they are designed for a particular fixed frequency. So the circuit is fixed here. So the selectivity and everything, all the performance, which are frequency dependent, all frequency dependent performance will be uniform for whatever the radio station I am looking for. Okay, it doesn't depend on the radio station now. So this, finally I will be having a very good output, and that output will be uniform over all radio stations. So that is the super heterodyne receiver block. Okay. So finally, based on whatever we have studied till now, an analog communication system can be briefly shown by this block diagram. I have the input signal, do the modulation, then I do up conversion. Now, what is this up conversion I am doing? This is the up conversion because here I am doing some down conversion. Okay. This FS to FIF is the down conversion. So in the transmitting side, I have to do the up conversion, just the reverse, because this reverse will be done. So modulator here will be working for FIF. Okay. So here the modulation will be done where the message signal will be first converted or translated to the intermediate frequency, and then it will be up converted from intermediate frequency to FS. Okay, then you do amplify it, amplify the power, send it through the channel, then you select it, you have the tuning amplifier, this tuning filter, then you have some amplifier here because the channel, the antenna will pick up a very feeble, the signal that will be picked up from the air will be very small in power. So you have to obviously boost it up. Then you have to do this down conversion. This is the down conversion stage. So you do the down conversion. So FS to FIF now. Here it is message signal frequency to FIF and then FIF to FS. Here it is FS to FIF and then you do the demodulation to the message signal frequency. Okay. So this is the basic, these are the basic elements of an analog communication system. Now the question comes that this carrier frequency, I was talking about carrier frequency, that even if I have a super heterodyne, this FIF, this intermediate frequency has to be translated to a higher frequency FS now or FC. FC is the carrier frequency. So how to choose this station frequency? How to choose this radio station frequency, the channel frequency? The channel frequency or the radio station frequency, it will depend on the distance and the location of the transmitter receiver pair. How far they are separated out, whether they are on the other side of the earth or not, all these things. We have to look into that. And then also we have to see that which communication system we are going to use, which is in our hand, which we can use. Okay. So depending on the availability of the communication system and depending on the location of the transmitter receiver pair, we have to decide the carrier frequency. For that, let us study about this, the mode of propagation, how the EM wave actually propagates in the in air basically. We are not talking about free space. Okay, so how it is transmitted or how it propagates. There are three modes of propagation. One is ground wave, line of sight propagation, and sky wave. Okay, what is that? Ground wave. What is that ground wave? Very low frequencies, extremely low frequency up to 3 kilohertz, very low frequency 30 kilohertz, low frequency up to 300 kilohertz, and medium wave up to 3 megahertz. Anyway, this demarcation of the frequencies are not a very crisp demarcation. There is no hard and fast demarcation like that. Okay, it is just we take this 3 because you know that frequency into wavelength is equal to your speed of electromagnetic wave, which is approximately equal to 3 into 10 to the power 8 meter per second. Okay, so I think you can understand why we are taking this frequency ranges. We are taking the frequency range boundary at 3 kilohertz, 30 kilohertz, 300 kilohertz. You can understand why it is so. Okay, because frequency into wavelength will be equal to 3 into 10 to the power 8 meter per second. Okay, so that's why this 3. Okay, however, you cannot say that exactly 3 kilohertz is extremely low frequency and 3.1 kilohertz is very low frequency. Generally, we cannot say like that anyway. Okay, it is just a rough demarcation. Okay, so anyway, these low frequencies, all these low frequencies of these ranges, they can travel using ground wave propagation. Okay, they actually cannot penetrate much through the atmosphere. Okay, that is the nature of this electromagnetic waves. They cannot go high into the air sky. Okay, they cannot go into the atmosphere. You cannot throw it upwards. Okay, they will always try to go above the ground. Okay, what happens here that in this case, okay, the earth this earth, okay, this earth and the ionosphere above. These two actually acts as the two plates of your waveguide. I have said, I have talked about waveguide earlier, that there will be two parallel plates and your waves will be propagated through that waveguide. So it is as if the ionosphere and the earth, these two forms a parallel plate of the waveguide, and the ground waves will be propagating between these two. So it is your ionosphere here, this is the earth here, and the ground wave gets propagated like this. So it will be following the contour of the earth. But the problem here is that it cannot go to a long distance. Because of this earth, the earth actually, any electrical signal which comes in contact to the earth, it dies out, means it is grounded. Any electrical signal, it gets grounded. Earth acts as a ground plane with zero potential. So all the electric field which will be traveling here, gradually that electric field will be dropping down. The electric field will be dropping down because of the grounding. Okay, so that's why actually the ground wave cannot go very far. So this type of propagation, ground wave propagation, can be used for a local transmission. For example, in amateur radio, students in different institutes, even in IITs, they do some hobby club. In the hobby club, they use amateur radio. So in amateur radio, you can use it, very low frequency. Then in submarine and all these things, where they do some communication in a very nearby submarines, underground, under the sea, because there you don't have a skywave, you don't have satellite. So there you use this ground wave. Okay, there only you use the ground wave and it propagates over the bottom layer of the sea. Okay, ground wave is used, but that again cannot be communicated to a very far off distance. Okay, ground wave dies out. Okay, so ground wave can be used there. And in radio system, I don't know whether you have ever listened to the earlier days radio, not the FM radio. I am talking about the earlier days radio. In the earlier days radio, we used to have something called medium wave radio station. And that medium wave radio station used to be for a local city on. Okay. So for Delhi city, there is a radio station and that uses the medium wave. So that medium wave can only be received in and around Delhi. That's all. Outside that, you cannot receive. Okay. So that was the ground wave, that is the ground wave propagation, which cannot travel very far away. Okay. Next comes the sky wave propagation. What is the sky wave propagation? Now in sky wave, we send short waves of the range 3 to 30 megahertz. This is the range of short waves. And here the signal coming from the transmitter goes to the ionosphere and it gets reflected from the ionosphere. It gets reflected from the ionosphere because of the charged particles in the ionosphere, it gets reflected. Okay, and you can see, since it gets reflected like this, it can cover the signal from one transmitter, can cover a large area in the earth. Okay, so it is very good for broadcasting. Okay, another thing you can see that because of this reflection, it is possible that even if you are on this side of the globe and someone on the other side, this side of the globe, okay, it can reach from this side to that side. Okay, they cannot see each other. They cannot see each other, but it can go from this side to this side. That is what the earlier days radio system used to use for transmitting radio signal from one country to another, from one continent to another. In fact, the BBC radio station used this shortwave, and because of that, we can listen to the radio of BBC, the BBC broadcasting station. We can listen to it. Otherwise, London is far away from here, and it is on somewhat on the other side of the globe. If we are somewhere here, London is somewhere here, like that. Okay, so they are out of it, is not in the line of sight also. So in earlier days, the radio station used to use this shortwave communication, the skywave communication, for broadcasting signals from one country to another, from one continent to another. Okay. Next comes the line of sight propagation. Okay. Line of sight propagation. Here the propagation will be in a direct straight line and it should be in the line of sight. If it is not within the line of sight, you cannot. Okay. For example, the television, TV station, you know that in a city, the TV station tower used to be on top of, means it will be very high, so that it covers the whole city and all the buildings in that city can receive the signals from that television tower. It has to be within the line of sight. Okay. So, and this line of sight propagation is possible in very high frequency. In fact, very high frequency cannot even get reflected from the ionosphere. They will penetrate the ionosphere. So, very high frequency transmission can only use line of sight. You cannot go for skywave there because it will penetrate the ionosphere. Okay. So that is what the line of sight transmission, the television stations used to use this. Okay, they use it. Okay, even now the local television center, say the Delhi television center, will be using this for covering television signal broadcasting in its line of sight. So it has to be within the line of sight. So obviously now the problem comes that if there is some obstacle in between like this, if there is some hill, and I have a radio station here, okay, say this is here, I have one radio station, say this is the radio station in Roorkee, okay, and on this side it is somewhere on the other, say not Roorkee, say it is Dehradun, okay, this is Dehradun, and then this is on the other side of the hill, it is somewhere, say in the hills, okay, say it is somewhere in the upper places, say Pauri. Okay, so suppose this is Pauri. Pauri is the place. So this is Roorkee, this is Pauri, and in between I have a hill. Okay, I have a mountain. So since line of sight cannot go, it is not within the line of sight because the hill is obstructing. Okay, so there, what I can do? I can then, in that case, I have to build a tower which is even taller than the mountain. But that is not possible, okay? Because it is not feasible at all. Possible means it is not feasible that I have a tower like this. So in this case, we can place one transmitting relay station on top of the hill. That you might have seen in many places. Even for radio station, television stations like that, we have something like that. You will be seeing that some the tower like this on top of hill, okay, on top of some mountains, you will see like that. They are actually the relay stations. What they are doing is that they are taking the signal from this side and then redirecting it on the other side of the hill. Okay, so that is how the line of sight communication can still take place. In case of Earth, again the line of sight problem will be coming, because from here, suppose I want to send some signal to London, or I want to receive a signal from London BBC. Okay. Now it is, since London is not in that line of sight, then in that case also I have to build towers like this. Okay. I have to build towers like this, large, tall towers. Again, that is not feasible. Okay. If two cities or two countries on the two other sides of the globe, there also a line of sight propagation is not possible. Okay, not feasible, because I cannot build very large towers like this. So in this case, a better solution, okay, obviously we can do relay stations, but there I have to have many relay stations in between. If it is between two continents, I have to have many relay stations like that. But a better solution to this is what we are using nowadays, is the satellite, is the satellite communication. What we do, I have a satellite like this, which is in the geostationary orbit. You know, it is in the geostationary orbit. We have many satellites. In India, we have the INSAT placed in the geostationary orbit. So I have a transmitter from here, which will transmit microwave frequency signal which will penetrate the ionosphere, very high frequency. It will penetrate the ionosphere and it can go to the satellite. The satellite will now redirect it from there to the other part of the world. Okay, it has to be in the, again, line of sight. Okay, it has to be in the line of sight. If not in the line of sight, then again I have to do the relaying it through multiple satellites. I have to relay it through multiple satellites. Okay, so these are some artificial satellites which are used for communication purpose, and they are called the communication satellite or ComSat. Okay,
Excuse me, sir.
so bolo.
Sir, in that where you told that the waves are reflected by ionosphere, which
Hmm.
property of the EM waves is used? Because the EM waves are not affected by electric or magnetic fields, so why they are being reflected by the ionosphere?
Okay, that you have to means there are some certain properties why it is not so. Why you are saying that it is not affected by the, there is certain something called boundary condition. Okay, now that one I am not at this point you cannot understand, because there is something called there are, I have told you something about three the four, sorry, not three, four Maxwell's equations. Okay, one of that equation, although I have given all those equations for free space. Sometime back I have given you four equations for Maxwell's four equations, and that I have given it for free space. But when there's some conducting boundary comes, the second Maxwell's equation, the, the out of those four Maxwell's equations, the second one is a bit different. It is not, I have, whatever I have given, it is for the free space. So there it is a bit different. So here actually the ionosphere, the charged particle in the ionosphere will be acting as a boundary, conducting boundary. Okay, and there the reflection will take place as if that boundary condition is it is not, it is violating the boundary condition of the free space. So it has to now conform to the boundary condition given by a conducting plane. Okay, so any electromagnetic wave, when it falls on a conducting plane, in fact the waveguide also is using it. I said in a waveguide there are two parallel conducting planes. How is that wave is getting reflected in it? It is because of that. Okay, so here also that same condition will take place. Now details obviously I can at this stage you cannot understand. Okay, so it is basically the ionosphere is acting like a conducting plate, and that's why it gets reflected. But again, it is only for a certain range of frequencies. For some other range of frequencies, it will penetrate through. Okay, got it?
Yes, sir.
Okay. Details obviously you will study it in third year, not now. Huh? So it is just to take it in that way, that it is like the conducting plane is like acting like a mirror. Only for certain frequencies, not all frequencies, but for certain frequencies it is acting like a mirror. Okay, and ionosphere, since there are charged particles in the ionosphere, it is like a conductor now. Okay, okay,
Yes.
so for satellite communication, however, the microwaves, they can penetrate through. Again, that you will study why for certain frequencies the condition is different. Okay, so they can penetrate through that ionosphere. Okay, and they will reach the satellite. Okay, and the satellite will basically, what it will do, that it will relay it back to one or more receivers on the earth. Okay, why I'm saying one or more receivers? Because for example, you have the DTH TV, okay, and there is one radio, one television station transmitting the message to the satellite, and from that satellite, the signal is coming to every house. Okay, so that's why I'm saying one or more receivers. Satellite communication system can be used for what? It can be used for relaying the telephone signals. Okay, That is what actually we are nowadays doing. That's why we are able to communicate with people in other countries also. Okay, so telephone signals, this STD, ISD, all these are based on satellite communication. Okay, in fact, that's why before the satellite was there is no STD, no ISD. Okay, only after the satellite and all these things came up, then only people could contact with each other via STD and ISD. STD, ISD are all via satellite. Okay. Then broadcasting television signals. Okay, that is direct to home television distribution also. Okay, is included in that. Okay, general television signals also can be broadcasted. Then communication links to many remote locations are also possible through satellite communication. And one thing that we use nowadays very frequently is the GPS, Global Positioning System. And that is what you do in Google. When you are traveling, you use the GPS system for locating your route and all these things, isn't it? You switch on your GPS and then it will tell you that in which direction you have to go, because that is using the satellite to find out your position, and accordingly it can give you the direction. Okay, so these are all based on satellite communication. Okay, so a satellite communication system, as you can understand, it will consist of a satellite. Okay, if that is a space vehicle, a ground-based control station will be there in the earth. Okay, and you will be having a network of many users who will be communicating through each other. So you have to have one control station on the earth, satellite is on the space, and you have all the users connected to each other. Then they are connected basically through the satellite, and which is controlled by the control station. This satellite, as I have mentioned just now, just some time back, I mentioned that the satellite is generally placed in the geostationary orbit. You know that a satellite in the geostationary orbit means with respect to the Earth, the position of the satellite is fixed. How it is helpful? Since the position of the satellite is fixed with respect to the Earth, then the antennas that I have to direct it towards the satellite, those antennas can be also fixed. That is what you do at your home. Na? At your home, when you are fixing the dish antenna on top of your roof, okay, then you fix it and you see that in which direction it should be pointed. You know that all the dish antennas in India are pointed somewhat towards southeast, somewhat towards southeast. You know why? Because the satellite that India is using, the INSAT, that INSAT is somewhere in the geostationary orbit, somewhere towards the southeast direction, because it was actually when it was sent, that satellite when it was launched from your Bay of Bengal, that side. I think it was from Sriharikota. Okay, it was launched, and so it was launched somewhere towards that direction, southeast direction. Somewhere it is above Singapore. Okay, somewhere there. Okay, so that's why we have to always point our dish antenna in that direction. And now, since the satellite is fixed there in that position, our antennas is also fixed. If the satellite had been moving, if it had been moving with respect to the Earth, then we also have to keep on moving in the direction of the antenna. Okay, so that is not possible again. So that's why we generally use geostationary satellites. Okay. In the satellite, we have a transponder. It is called transponder. What is that transponder? Transponder, it is basically the relay, okay, which will be receiving the signal from the Earth and then relay it back to the Earth. Okay, so it is somewhat like a reflector, you can say. Okay, it is reflecting the things. Okay. Then there is the uplink, that is Earth to satellite, downlink, satellite to Earth. Obviously, that link is wireless link. There's no, it is not wired link. But for that link, as you have now, by now you have understood that I have to have a particular frequency allocated for that uplink, okay, and I have to allocate another frequency for the downlink, okay. So two different frequencies are used for uplink and downlink, okay. So again, this frequency division multiplexing is coming into picture here, okay. So the transponder will collect the signal with some frequency and then relay it back to the earth at some other frequency. So it will do demodulation, modulation, all these things. The transponder will do it. Footprint, this term you will encounter in satellite communication. The footprint is the area that the satellite can cover, the area on the earth surface that it can cover. Obviously, INSAT cannot cover the earth's surface which is on the other side of the globe. It cannot cover. Yeah. So like that, if every satellite has some coverage area, that is called the footprint. And you can increase the footprint, the area of the footprint you can increase if you have multiple antennas, okay. So one antenna will be having a very small coverage area because the antenna is directed, it is directed, na? It is so if you have many antennas on the same satellite, then obviously the coverage area will be a bit more. So we generally use multiple antennas, and we also use multiple transponders, one transponder for every channel. So like that. So that is how the whole communication system in the satellite system works. Now, okay, these are some of the basic things about all those transmission and all these things. Now coming to some signal types, what are the different signal types we are using in communication? Okay, till now you have seen that mostly what we were using signals, the message and voice. This is what we were talking about. What is a signal? Signal is basically, it is a function of one or more independent variable. In fact, the sound itself is a signal, but that is not electrical signal. That is a sound energy. Light itself is a signal, but that is light energy. So all these are signals. Basically, a signal is any function is a signal. Okay, but they may be of different energy form. Electrical signals are only those signals which are in the electrical energy form. So it is electrical signals, you can define it as voltage or current, which is a function of time, or it is a function of space. I will come to that. What is function of space? So it is electrical signals are voltage which is a function of time or space, and they can be represented as function of frequency. That is how we represent the spectrum. I have already said about spectrum. So that is how we represent a signal in its frequency. That what are the frequency contained in that signal. That is the spectrum. One dimensional time domain signal is time domain, so it is a function of time. That can be represented in the form of one-dimensional frequency domain signal. This is the spectrum. This is what I was showing you. All the spectrum and all these things I was showing you. The signal was basically my speech signal, which can be plotted as a function of time, because when I am talking with time my voice is changing. So that can be plotted in time, and then I can analyze it. I can find out what are the frequencies present in it, and accordingly I can sketch the spectrum. Okay, so that is the one-dimensional frequency domain representation. This is the spectrum of it. Okay, two-dimensional spatial signal, it is called the spatial in the spatial domain. This is actually, say, when I am taking a picture. Okay, when you are taking a picture in your digital camera, what it is doing, whatever the scene is there, the scene is actually in space. Okay, the scene is in space, that is projected onto your camera. So in camera, it is now projected as a two-dimensional figure. Okay. So there you have XY coordinate in your camera. Okay. And corresponding to the intensity or the brightness or the color of the picture that is falling on you in your inside your camera from outside. From the outside world, the light is falling in your camera. Depending on the light falling on your camera, you have some particular electrical signal produced, which is stored in your digital camera in the form of a digital signal, digital picture. Okay, so that is actually how your digital camera is working. Okay, here the outside light energy is converted to electrical energy, and that electrical energy is now stored in your camera in the form of a file, in the form of a digital file, which you can now read it in your computer. So that digital picture which you are taking in your using your digital camera, that picture is a electrical signal, but it is not a function of time, but it is a function of space, XY coordinate system. Okay, XY coordinate system. So that's why I am saying that electrical signal can be also a function of space. So that is a two-dimensional spatial domain, SXY. This is my picture. Okay, I can represent the picture at every XY position. What is the value of my signal, of my picture? Okay, SXY. And again, I can also find out the frequency contained in that, and accordingly we do two-dimensional frequency domain representation of the spectrum. So that will be a two-dimensional spectrum. Okay, SU. U and V are the two frequencies. One is called the horizontal frequency, the other one is called the vertical frequency. Okay. Some examples of these electrical signals are ECG, EEG, then 2D ECG. So that is again two-dimensional signal, 2D ECG. So that 2D ECG is spatial domain. USG, it is also 2D. You have seen USG. So these are all electrical signals. These are all electrical signals, but again, you just print it. USG that you see, it is basically the electrical signal, then you print it for your viewing. Okay. But otherwise, it is an electrical machine that will be doing all this, picking up the signal. Okay. MRI, this is also electrical signal. CT scan, okay. Seismic images for, seismic signals are used for exploring the oil, whether there is oil underground, whether any other mineral is there underground. Then for earthquake also, okay, to find whether there is any disturbance below the earth, whether some earthquake is about to come or not. You use the seismic images, seismic signals. Okay, so these are all different types of signals. But in communication, we are not concerned about all this ECG, EEG, and all these things right now. What we are concerned about is basically the message signals. We are talking about message signals. Now, these message signals are broadly of two types: analog, continuous time, and continuous amplitude, which we were talking about till now. Okay, and the other one is digital signal, which is the discrete time, discrete amplitude, and binary coded. Okay, so that we'll talk about afterwards. Okay, what is a digital signal? Okay, message signals, text messages. We have started with telegraphic signals. That time it was text which we used to transmit. And how we used to transmit, as I said, we used to transmit it. Every alphabet used to be coded with some Morse code. Every Morse code will have some dash dot. So dash used to be represented by a long pulse, dot used to be represented by a short electric pulse. So that is how the text messages used to be represented in the form of an electrical signal. Okay, but nowadays obviously you are not using a telegraph, you are using emails. And emails are what? Emails are basically, again, this you are sending some binary bits Okay, some bits you are transmitting for every character. Every character is transmitted over your computer network in the form of bits. Okay, we'll talk about that afterwards. File transfer protocol also you use. Okay, a file transfer protocol, FTP, used for file transfer. So these are all text messages. Similarly, speech, audio, these are also message signals that is used in telephonic system, radio broadcasting, TV sound, mobile phones. Okay, and you know the bandwidth of our voice is 3.4 kilohertz, audio bandwidth is 20 kilohertz. Okay, this is what you mean. Image, video, as we said many a times, TV pictures, video phone, they also use this image video, image and video downloads. Okay, that is what you are downloading nowadays in your computer. So they are also image and video signals. This bandwidth in TV we use 5 megahertz, although up to 4.2 megahertz bandwidth is good enough. Okay, but we go for a better one. Okay, my 5 megahertz. Okay. Now this is the just again going back to the progress in the last century. Some we have talked about the progress till the 19th century. Now in 20th century there had been actually tremendous development in communication sphere. Many things, multiple things came up. 1927 television came up. Okay, so before that no picture transmission, no picture communication was there. 1927 picture television, this television came and picture also came up. Means before that actually we were having only text and speech, but image video, that communication came into being when television came up in 1927. Then you have video phones and all these things. Then mobile telephone also came up sometime in 1946, but that was of limited capacity and it was used for only very specific purposes. Then satellite communication also came up. Then you see 1964, around that time fiber optic telecommunication started, and using that fiber optic telecommunication, computer networking started. So basically the digital communication and the fiber optic and computer, all these things mixed up. And then in 1969, from that actually we had the recent days communication, that is the digital communication, computer communication. Okay, and we still have the computer communication, mobile communication, and satellite communication. These are the three things which are still dominating the communication world nowadays. You can see that internet came up sometime in 1983 when ARPANET was developed in US. Basically the military, the defense of US, they developed this. And in India around, after some time, around 1990, the ERNet came up in India. That was the internet system in India that came up in that time. So these are the developments during that time. So just finishing up today's talk with the mobile phone system, just with this, I will finish up today. Mobile phone system, you know, what you have, that a geographical area is divided into small cells. Okay, so you have small cells. You have one mobile user, another mobile user. They will be using one frequency for uplink to the base station and another frequency for the downlink. Okay, so like that, in one cell there will be multiple frequencies should be there. The base station will use some frequencies. So if suppose there are 20 users in one cell, so the base station will be using 20 frequencies for connecting to the 20 mobile users downlink. It will have another 20 frequencies for uplink from each of these 20 users. So total 40 frequencies should be allocated to one cell. Okay, so every cell will be using a set of frequencies and that are shared by the mobile users in that cell. Okay. However, there one good thing about mobile communication is that these frequencies which are used in a cell can be reused. Only thing is that you cannot use it in the adjacent cell. So some frequencies which are used in this cell can be used in some cell far away, but not in these 6 cells around this. Okay, it cannot be used. So basically that is how the reuse is possible, and hence multiple users can be accommodated. That is one good thing with mobile phone. Smaller cells, many so in one cell you can have, say, if I have 40 frequencies, so basically total 280 frequencies will be good enough for covering the 7 cells, and these 280 frequencies can now be reused. Whatever frequencies I have used here can be used again here. Okay, like that. Okay, so that is what. So now you can see so many users can be accommodated, but with using only 280 frequencies, you can keep on reusing. In a large area, many users can be there. Okay, 20 users in each cell, like that. Just it is an example. How the mobile system works is like this, that when there should be one mobile switching center. This is actually the controlling center, which will allocate the frequencies to defined cells, the base stations, the mobile users. This is which is controlling the frequency allotment. Okay, this mobile switching center. So when a user in a particular cell, okay, user is moving in a particular cell, user wants to call someone. So that user will basically get connected to the base station of that cell. And this base station is directly connected, already connected. It is connected to the, all the time it is connected to this control mobile switching station. Okay. So this base station will send that link, means that it will send this request that this caller wants to talk to someone in the other cell. Okay, so or maybe in the sensor. So this base station will now send that request to the mobile switching center, and the mobile switching center will now connect it to that to the called party, while the called party may be in the other station, other cell, or maybe in the same cell. So it will connect to that base station of that cell, and then that base station will connect it to the user of that cell, called party of that cell. So this is how the connection takes place. Okay, and mobile switching station, what it is doing, it is allocating some frequency accordingly. It will keep on allocating the frequencies which are free. Okay, that's why sometimes you will see that nowadays it doesn't happen that much, but in earlier days it used to happen that you want to call someone but you are not getting the call. The reason is that no free frequency is available. No, if no free frequency is available, then it will happen. Okay. So that is how the mobile switching center will be allocating the frequencies. So the dynamically allocated to defined users. It is dynamically allocated, and it keeps on doing the connection between the users. Okay. So you can see here, this is another picture here I am showing that this car wants to communicate with another car in the other cell. So this car will be transmitting it to this base station, its request. This base station will redirect the request to the mobile telephone switching center. The mobile telephone switching center will now connect it to this base station, and this base station will now do the connection, do the connection to the intended receiver. This is how the connection is established. Even if you want to call someone in the landline, this mobile switching station will send a request to the public switched telephone network system, and then from that public switched telephone network system, it will get connected to the landline also. It is also possible. If someone is moving away from one cell to the next cell, then obviously the frequencies allocated in this cell cannot be used anymore. So when this person, this car, moves to some adjacent cell, obviously it will move to adjacent cell only. It cannot jump to a far off cell. When it moves to its adjacent cell, then some handoff will take place. What is that? Whatever the frequency it was using while communicating, that frequency will be released. That frequency will be released, and it will be immediately, it will be allocated a new frequency corresponding to the other cell to which it has moved. And again, this will be controlled by this switching office. Okay, this mobile telephone switching office will control that frequency allocation. So new frequency will be given. So this is called handoff. Again, in earlier days, there used to be a problem with handoff. Okay, so sometimes when you are moving, sometimes your call will get dropped. You will be not able to connect. But nowadays, with advanced technology, advanced research, that has been minimized. This call dropping has been minimized. Okay. So next class, I will just give a brief idea about the digital system of communication, and I will give a brief idea about the television system. Okay, and hopefully on Monday we will be completing the syllabus. So in next Friday we will be having a small quiz. Okay, so that's all for today. So again, I will post it. I will post this all these slides. You can go through all these things. Okay. Any question? So you can, if you have any question, you can ask me on Monday. Okay. And otherwise you can leave. Okay.
Thank you, sir.
Okay. Bye.
Thank you, sir.
Okay. Bye. Bye all of you.